All right, these are going to be the notes on 5.5. We have 2 days of it, and then we're going to test on 5.1 to 5.5 all at the same time. We'll talk about when that is and go look at the calendar when I'm done with these notes. So open up your notes to this page, and we are going to be taking the derivative of exponential functions, that's something to the x, when the base is not e. So we already know and have proved that the derivative with respect to x of e to the x is always e to the x. It's the only function in the world where its derivative is the function itself, and we proved that yesterday formally. And similarly, we have the derivative with respect to x. I'm using this notation now. It's an old-fashioned notation, but I like you to get used to all the different notations. That this is e to the u times the derivative of u with respect to x. And that we've done, that if we're doing the derivative with respect to x of e to the 3x minus 1, it's simply e to the u du, or 3e to the 3x minus 1. That we already know. But the minute I change out that base and have it not be a e, but maybe a 3 or a 4 or a 7 or an 11 or a pi, what is the derivative? So I'm going to just write it down for you, and then I'll prove it or show it to you. This is ln a to the x. By the way, that works for your e as well. If you were to think of, well, it's ln e to the x, ln e is 1. So it holds for all bases a, where a is a constant. Likewise, my derivative with respect to x of a to a function of x, it's still going to be ln a. It's still going to be a to that function, and then you can probably guess it's going to have the derivative of u with respect to x. And they're pretty easy to use, but I don't like to just give it to you like that. I want to prove it. So let's go over to this one, and let's do this formally. According to this model right here, the derivative of 3 to the x should be ln 3 times 3 to the x, and it is, and you don't have to prove it every time, but we're going to take a formal approach to it. Let's call our function y equals 3 to the x. Invariably in pre-calc and beyond, when x is your exponent, we get it out of there by taking a natural log. In derivatives, this is called logarithmic derivation. Sounds good. It rolls off the tongue. Anyway, I'm going to take ln y equal to ln 3 to the x. Keep in mind, my goal is to find the derivative, so I want to get y prime, but I'm just starting off by getting that x out of the exponent. And the reason I take the natural log of both sides, not only because I can, not only because I like to take natural logs, but primarily because the exponent comes out front when you're doing logarithmic functions. Now remember, I have really done nothing. I have not taken a derivative yet. I'm going to right now. I'm going to take the derivative with respect to x of the left-hand side, which would have to equal the derivative with respect to x of the right-hand side. And the right-hand side is ln 3 times x. We've done this one quite a bit, that the derivative of ln y is 1 over y times y prime, or equivalently, y prime over y. Boom. Just like the derivative with respect to x is 1 over x, when I have a function of x, remember it's 1 over that times its derivative. So I've got y prime over y. The derivative over here, ln 3 is a constant, so it's like I'm telling you to take the derivative of a constant times x. If that was an 8x, you would have no issues telling me that its derivative is 8. Well, ln 3 is a constant as well, so its derivative, ln 3 would be the derivative of ln 3x. Now my goal was to get y prime, and so I'd have ln 3 times y. Well, y is defined as 3 to the x, and that will always happen? Watch me go change this now. Instead of having a specific proof for a specific base, if I go change this to an A for any base, then this would have been an A, 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 and it would have been ln A to the x. Do not prove it ever again. It will always happen. So the derivative of 8 to the x is ln 8 to the x. It's nice and easy. All right, so let's go down here and practice this in its straight up form. So example number 1, I've got a base of 7. So just like if that had been e to the u, I'd say that its derivative is e to the u du. That's exactly what I do here. But my base is 7. So my y prime becomes ln 7. When it's e, there actually is an ln e there, but ln e is 1. So I do ln 7 times 7 to the 2x minus 1. This is ln a to the u, right here, ln a to the u, and now I have to remember to multiply it by the derivative of this function. Sorry, I crossed it out, but which is 2. So when I write this nicer, I get 2 ln 7 times 7 to the 2x minus 1. You always should put your whole constant chunk out front, and it's as easy as that. So let's go do another one. This is a quotient, so it lends itself to the quotient rule, and I'm taking a derivative. So my f prime of t would be low d high. Well, what is d high? That's an exponential function. It'll be ln 3 times 3 to the 2t times 2. There's my low d high minus high d low, so that's just going to be 3 to the 2t. The derivative of t is 1. I'm going to draw a line and square below. So my derivative becomes f prime of t is equal to, let's go factor out a 3 to the 2t because it makes it pretty. So I've got 3 to the 2t times ln 3t. Well, actually, that's ambiguous written like that. Let's make sure we've got all our math. Let's write it like this just so it doesn't look like ln 3t. And then what would I have here? Oh, and I've got a 2 in this factor also, so let's do 2t ln 3 minus 1 all over t squared. So all I did was quotient rule. I applied my base other than e rule, and I factored out a 3 to the 2t from both parts of the difference. And this is my final answer for the derivative. So let's move right along here. We also know, not only do we know what the derivative of e to the x is, and now a to the x, we've also know what natural log's derivative is. It's 1 over x. And remember, when it's u, it's 1 over u times du dx, or equivalently, u prime over u. But what if I go, oops, I forgot my dx's on here. Let's go throw those on here. What if I have a base that's not e again? So I don't want ln, maybe I want to do log base 4. Well, I'll show you what happens with a specific example, and then we'll shorten that up to a general rule. Let's again pretend that we don't know, and we're going to go work this out. If I have log base 4 of x, I could say that 4 to the y is equal to x. That's just using my properties of logarithms. So I'd have 4 to the y is equal to x. And I would take the natural log of both sides. I'd then be able to bring the y out front. And I'd get y ln 4 is equal to ln x. So just using the property of logarithms. Next, what I'd do is I would take the derivative of both sides with respect to x. And see if I can squeeze this in here. Now what I've got is ln 4 is a constant. It comes out front. dy dx is just y prime, or you can leave it as dy dx, so I'm going to write it as y prime. So I actually get ln 4 times y prime is equal to the derivative with respect to x of the natural log function is 1 over x. Recall my goal is to solve for y prime. So when I divide both sides by the natural log of 4, I get y prime is equal to 1 over ln 4 times x. Now look it. When the base was e, we said the derivative is just 1 over x. Well, watch, if I replace that base with an e, ln e is 1. So it's a really easy way to remember it. If you know that the derivative with base e is 1 over x, then with base 8, it's actually ln 8 on the bottom. So it's a nice, easy one to remember. It's 1 over ln a times x. And again, here's e's derivative right there. So it's easy to remember. The College Board doesn't ask this one hardly ever because they don't want you to get these wrong because you forget. I'll have them on the test, but I'll probably allow you to have these sitting in front of you, although they're pretty easy to derive. Similarly, when we have, say, the natural log of u, and we've got that format, that's exactly what's in this one. It's the same thing. It's 1 over u. And then you've got du dx, so you can think of u prime. The only difference is we throw an ln a down here in the denominator. And I could prove that one as well, but I don't feel like it. So I don't want to. You could probably figure out what it looks like. It's very resembles this one quite a bit. So look at all this. It says be careful with the differences between all these because they're very different. The derivative with respect to x of e to the e, well, e to the e is the constant, and a derivative of any constant is 0. Some kids will use a power rule on that or natural log to bring the e's out front, but your variable of change is x. E is always a constant. The derivative of e to the x is just e to the x. However, the derivative of x to the e, again, e is a constant. It's like x to the 4th would be 4x cubed. Well, x to the e would be e x to the drop it down 1. So be very careful with these. The trickiest of these being this last one, because x to the x, we haven't given you a derivative for that, but you should be able to monitor and adjust whenever the x is in the exponent. We can always begin by defining the function as y, realizing that I'm looking for y prime. Logarithmic differentiation will be applied. I can get that x out of the exponent. My goal now is to take the derivative of both sides with respect to x, which gives me 1 over y times dy dx, or y prime over y. And then over here, I've got myself a little product rule. First, d second, plus second, d first. So when I'm all done, I've got y prime over y is equal to 1 plus ln x. And what I'm going to do is, instead of writing y prime over y, I'm going to multiply by y. But y has been defined as x to the x. So this is my expression for the derivative. Note how much more difficult that was when the variable was both the base and the exponent. So it says you don't need to memorize these. I've given them all to you, but I think you should memorize them based on their derivations, but you can go ahead and look at these. So if I do the derivative with respect to x, let's just say log base 8 of 4x minus 1. I'd recognize that this is this one, and I would just simply go and do 1 over ln 8 times the function, which this is u, this is a, times the derivative of the function, which is 4. And it falls out real nicely from that pattern. So you can go ahead and look on this. This isn't one of the most important topics we've ever done. 3 more examples and then I'm done, and I'm doing ones that I think you'll have questions on when you get to the homework. So I do have another base here. I'm doing log base 3, but that's a big, ugly function inside of here that I'm supposed to be using as my u. So remember what we said when we have these like this. We use our properties of logarithmic expansion. Another fun thing to say. I'm getting a lot of stuff in my favorite word bank today. Logarithmic differentiation. It's got a lot of syllables in it. I'm going to break this sucker apart. First and foremost, it's a quotient. On the top is a product and also a power. So what I'm going to do is expand this out, and you guys did great on your quiz when you expanded, so I'm just going to write it all out. It'd be ln x plus 1/2 ln x minus 1 minus ln 2. So use your logarithmic expansion properties to blow that up. And then we will take the derivative of both sides with respect to x. And that's my goal. I want to figure out what's y prime. So when I take the derivative of every part of the sum and difference by itself, first of all, I have log base 3 of x that I am taking the derivative of. So we need to remember how we take the derivative of log base 3 of x. And if you need to go look at your sheet, go ahead. All right. If it were ln x, it'd be 1 over x. But it's not ln x, it's log base 3. So we do ln 3, should be in parentheses if I'm going to write it correctly, and now it looks like crap, so I'm going to fix it. But you can go ahead and look at the sheet on the previous page, but this would be 1 over ln 3x. Notice how easy it is to remember it, though, if you just kind of pretend it's ln, and you go, oh, it's 1 over x, and then you just throw an ln 3 down there in the denominator. Plus, I've got 1/2. Natural log's derivative is 1 over x. It's actually 1 over ln e, just like over here, but ln e is 1. So, I digress. 1 over x minus 1 times the derivative of u, which is just 1. And then last, ln 2 is a constant. The derivative of constants is 0. So right over here is a beautiful expression for the derivative of my big ugly functione. All right. Question of the year. We've had it a zillion times. Equation of the tangent line. You should be rock solid on its process. I told you at the beginning of the year when we first had this question that we were going to have it a ton. The only thing that changes is we always need a, yell it, we always need a, you know, I'm not moving on until you respond to me. So 1, 2, 3. We always need to have a, no. In order to write an equation of the tangent line, you must need, find, or be given a, thank you, a point. Got it. And then we always need to be given or find the what? The slope of the tangent line, aka y prime at that point. Let's begin. So point slope form, y minus the y I know is equal to the slope there times x minus the x I know. The kicker to these is always how do I get the slope there? It's always a derivative. The functions just keep changing as we progress through the book. So I need to take y prime, which is log base 10 of 2x. Well, if it was ln, it'd be 1 over 2x times the derivative, or du dx, but it's not. It's base 10, so I throw an ln 10 on here. Or, if I can't remember that, I go look, and then these cancel. It's actually 1 over ln 10 times x. I need to calculate that derivative at the specific point 5, 1, which means mine is going to be 1 over 5 ln 10, which I don't want to go calculate on my calculator, so I'm just going to write 1 over 5 ln 10. I'm just going to leave it like that. Last up, I want you to star this, and if you are sleeping, you should wake up now. I'm going to put one like this on the test. It is worth 5 points. Every year, I have to give a huge chunk of zeros because kids don't go back and look at one like this. There's going to be one on a practice assignment, but this is one of the harder derivatives to take. College Board will not ask you to do this on the AP exam, but Mrs. LaRude will ask you to do it on her exam. I might change it to cosine x, and I might have it to the 4x or something, but the exact same process. So it would help if I had put directions on here. We are trying to find y prime, aka take the derivative of the function. All right, here we go. Universal rule. When the variable is in the exponent, we almost always get it out. In order to do that, we must take a log of both sides. Our best friend in log world is ln. Our second best friend is log base 10, but ln is the winner almost always. So we're going to take the natural log of both sides. That is going to allow us to put the exponent out front. And I'm going to have the natural log of my function is twice x times the natural log of sine x. Don't lose track of what I'm trying to do. I'm trying to find the derivative, and I've not even begun. All I've done is applied some logarithmic properties so I can get that stupid exponent out of there. Now what I'm going to do is take the derivative with respect to x of ln y, which we've done a bunch, and then over here the derivative with respect to x of twice x ln of sine x. This is impressive, right? It looks good. I love it. It makes me all warm and fuzzy inside. All right, here we go. What is the derivative of the natural log function? It's 1 over u times u prime, du dx, y prime. Either way, y prime over y. Over on the right-hand side here, I've got an oldie but a goodie, a good case of the product rule. So let's go do that. First, d second. Natural log function's derivative is 1 over u du dx. Oh, there we go. So first, d second plus second, d first, which would just be 2. Let's go clean up the uggies here. We've got y prime over y is equal to twice x. Cosine over sine is tangent in disguise. Cotangent, sorry I lied, is cotangent in disguise. Plus 2 ln sine x. All right. Now my goal, again, don't lose track of the end goal. My goal is to figure out the derivative of the function. So if I multiply by y, I'll have it. So my answer is 2x cotangent x plus 2 ln sine x. My sub's probably getting a headache. I don't know. I'm not, though. This doesn't give me headaches. This makes me feel very happy. All right. What was I doing now? Oh, yes, I was multiplying by y. However, I want my derivative all in terms of x. I don't want to throw a y in there. So let's go back up and see what y was defined as. Oh, boy, it's this. You know you're smart when your work takes up the whole smartboard. Y is sine x to the 2x power. Sine x to the 2x. And I'm done. I could actually factor out a 2 maybe, but why? It's good. I like it a lot. So what's our homework? And I know it's hard to do homework on a Friday, but I would like you to show my substitute what it's like to sub for an AP calculus class where they all get out their books, maybe find somebody to work with, and they all get cracking at it. I think it was written in your packet, but I can't find it. Let's see. Let's go back, by the way, to the schedule, because I had promised that at the beginning of the hour. So let's go slide back on up here to, well, what the heck? Oh, the schedule's on the other note packet. All right. Well, here we go. The assignment is page, it's on the front of that other note packet. It is page 368. And it will be 41 to 73 odd. Make sure you show me all the work on there. 41 to 73 odd. If you also look at the schedule, there is a test scheduled for Thursday of next week. It will be on sections 5.1 to 5.5 with almost nothing on 5.3 because we really didn't do much in there. So Monday will be a finishing 5.5. Tuesday will be review. Wednesday will be review. Test on Thursday the 5th. Over and out. Peace out, Girl Scout. Get your books open, all of you. Anyone without their book open and working and the sub writes your name down, you get an F. That's it. Even if you had an A, I'm going to give you an F. Just kidding.